This video will look at the hypothesis testing for a known population standard deviation or a large sample. We're going to work with example 1 out of the class notes. The sociologist wishes to see if it is true that for professional women, the average age when their first baby is born is 28.6 years. The sociologist selects a sample of 36 women. For the sample, the mean age when their first baby was born was 29.2 with a standard deviation of 3.1. At alpha equals 0.05, does the evidence support the hypothesis? All right, step 1 in the traditional method of hypothesis testing is we need to figure out what the hypotheses are. So in this case, the researcher just said the age when their first baby is born is 28.6. There's no at least, at most, nothing like that. So in this case, we're going to have a null hypothesis of mu equals 28.6 and an alternative of mu does not equal 28.6. Now, in order to move on to steps 2 and 3, we need to pick a statistical test. And keep in mind that the rules for this are very similar to what we had seen with the confidence intervals in the previous chapter. We prefer the Z version of the formula, but we have to meet the criteria. And so the first criteria for that is if we know the population standard deviation. In this case, we know a standard deviation, but it's of the sample. So we don't reach the Z version on that criteria, but we have a sample of 36. So we are able to reach the Z version based on that criteria. Now, with alpha equals 0.05, that equates to a 95% confidence interval. What we can do, and I show here in the notes a couple different ways you can do it, but basically what we want is the Z values that are going to give us 95% between them that are centered about 0. And you could either do that looking at the Z table and figure out it's negative 1.96 to positive 1.96, or the easiest way with the Blumen book is to go to the T table, go to the very last row, and see that Z or infinity row, and there you'll see a critical value of 1.960. This is two-tailed, so we need both positive and negative. All right, now, that's step 2. Step 3, we need to calculate the test value or test statistic. And this formula looks the same as what we had seen with the central limit theorem. Z equals x over bar minus mu in the numerator, sigma over the square root of n in the denominator. All right, in the numerator, x over bar is the sample mean, 29.2. Mu is the population mean, 28.6. That's what we're comparing against. That's what we will see in our hypotheses. Sigma is the population standard deviation. In this case, though, we don't know that, but we have a large sample, so it is permissible to substitute in the sample standard deviation. So we put the 3.1 in there. Sample size 36 goes in for n. Do the square root, do the division again. We get a critical value of 1.161. Now, we had critical values of negative 1.96 to positive 1.96. 1.161 is in between those two values. It's not out in either tail, it's in the middle. So the middle is the non-critical region. Our decision is we do not reject. Keep in mind, the decision you make in hypothesis testing always refers to the null hypothesis. So what we are not rejecting is the idea that the mean, or mu, equals 28.6. So my summary there is the average may well be 28.6. Now, part 2 of this would be we could actually calculate a p-value for this, and we'll talk about p-values more. But to do that, the easiest way to do it is with Excel, with the norm.sdist function. I took and used the negative of our test statistic, negative 1.161, and that gives me 0.1228295. That's the area from the left, in the left tail below 1.161. If I look at the same area above positive 1.161, it would be the same amount because the standard normal is symmetric. So if we multiply that by 2, the 0.1228 times 2, you end up with a p-value of 0.25.